Welcome to the next episode of Quarantime. We're so happy to have you back. And in your chat really quick, I'm going to just say hello to some of the locations that we've seen people saying where they're coming from. We've seen people from all over the US, from Canada. Yesterday, we heard from people in Brazil and Italy. And it is so exciting for us to be able to share science with all of you. Thank you for tuning in.
So something kind of interesting happened last night in the state of Utah. So I'm curious, did you feel an earthquake?
Oh, yes. Was it early this morning or was it last night?
I'm actually not sure the
I think
time.
it was early this morning.
I think I read that it was a 5.7 on the Richter scale.
So definitely some
So
going on.
If you felt an earthquake, let us know in the chat, because that's not something that happens very often.
Nope.
It's kind of cool.
Nope. If it is your first time joining us, and I want to give a special welcome too, if you're watching the replay later on, we have a format here of having a science demonstration, and then we have a challenge, and then we'll have a math lesson, and in between we have some other fun things going on, and we hope you enjoy this. And there is a little worksheet that you can print out that will sort of guide you through, and Science Mom Krista is going to put a link in the chat there. We do have 3 other people of our team who are in the chat, so Science Mom Krista and Science Mom is over in Facebook. Science Mom Liza and Science Mom Emily are on YouTube. And you got to watch out for Science Mom Emily. If you have a question that you really want answered and you put do copy and paste, and then you just keep pasting it into the chat over and over again, Emily will time you out so that you can't comment for 5 minutes. So watch out for that.
Indeed.
Now, one other quick announcement thing that I wanted to comment on, we have had a few people ask if we're going to be able to get captions. We don't have the resources, either the time or the money to pay somebody to caption yet, but it's high on our list. We would love to be able to caption these live streams, and we'll do that as soon as we have the resources to do that. Anything else we want to say before we launch right in? I'm
hoping on the replay and say YouTube that the auto captions will show up.
There will be some auto captions, but it's helpful to have someone go back in and correct, because sometimes it makes mistakes. All right, so let's get going with our activities today. Today we are going to be learning about inertia. And when people talk about inertia, they often talk about it as in something doesn't want to move. You know, it has too much inertia, it's not going to move. But when we're talking about inertia as scientists, we often talk about it referring to what Isaac Newton first came up with. Newton came up with laws of motion. And to help you explain and understand those laws of motion, I'm going to put on an inertia hat. Now, I know this does not look anything like a hat. It looks rather bizarre, right? But if I scoot you back just a little bit so that I can get this hat on, and then stand back here, you can see that it balances on my head really well. And the first law of motion says that an object in motion wants to stay in motion. So I give this hat a little push. You can see that these two this orange, red, and green ball, they're orbiting around my head like planets going around the sun. But an object at rest wants to stay at rest. So my hat will stay resting even if I spin around. And because I don't spin around perfectly still and my head's moving, it doesn't always, usually it'll stay with the red on one side and the green on the other side. Let's try one more time, see if I can do it. Almost. I think my hair is kind of helping my thing to move too, because it's in a ponytail and there was like a little bump there. But anyway, inertia hat, lots of fun. And I do have a video that shows you how to make your own inertia hat. We just made it out of a wire. But the big thing here to know about inertia and to remember is that an object is either going to have the inertia of being in motion or staying at rest. And if you've ever noticed in the morning when you're sleepy and someone says time to get up, there's sort of this resistance to being like, oh, but I'm resting, I want to stay resting. And if you're outside playing and you're running around, you have the inertia of being in motion. And when someone says stop, you don't really want to stop. You want to keep moving. Well, every object is like that. And if something is at rest, it wants to stay resting. And if something is in motion, it wants to stay moving. And so we are going to do several fun activities. But before we do our fun activities, there is one frequently asked question that I want to address really fast, and that's what about the drawings and where can I share them? So let me just show you. Yesterday's drawing prompt was to draw something fantastic outside your window. So to take the view from your window and then draw something unexpected. And it could be magical, fantastic, some sort of fantasy type element, or it could just be wacky, like Dr. Seuss's Wacky Wednesday book. So if I were to do it from my window, I live in Nevada, and outside in my front yard, I have cholla cacti. And these cholla cacti are really spiny. Sometimes they're called jumping cacti, because if you walk too close to them, and they touch you just barely, the spines will come off and get you. And so if I were to draw a Wacky Wednesday out my window view, it would be a cholla cactus jumping on a trampoline. And now I'm going to share with you a couple of the wonderful drawings that we saw from you guys. So here we have a wonderful picture of, it looks like a very creative alien in a pond. I love this one. Our next one is three-dimensional. They actually built a little window out of popsicle sticks, and then we've got a fantastic little creature peeking out from behind that window view. And then we'll share one more before we go on to our demonstration. This one, you can see, I love the colors and the detail on this one. The little fairies there.
Yeah. So where did those get submitted?
So if you would like to share your pictures we have a couple places you can do that. You can post them on Instagram. And if you want to share them, I think the best hashtag is to do Science Mom Squad, hashtag Science Mom Squad. Quarantime is starting to get busy with a lot of other stuff. And so when I search for Quarantime, I'm not seeing just your pictures, I'm seeing a lot of other things as well. And then on Facebook, on my Facebook page, I make a post. And in that post, in the comments, I invite you to share your pictures. And you can see and comment on other people's pictures too. And it's really fun to see all the creativity and the things coming in. And now let's take a look at several inertia activities, because an object at rest wants to stay at rest. An object in motion wants to stay moving. And if we come over here to our table, I have a couple fun things set up. The first one we're going to do is called the egg drop. And you can do this with a real egg, but I like to do it with plastic Easter eggs filled with Play-Doh, because then they're not quite as breakable. So here we have a plastic egg filled with Play-Doh, and it is on top of a toilet paper tube. And that toilet paper tube is on top of an aluminum pie plate. And then it's on a cup. And if you apply a force to the cup, the plate, it will move. It will move out pretty quickly. And that force, when it moves out, will then move out from underneath the egg, and the egg will drop right into the cup. So here we go. I'm going to scoot this back just a little bit so you can see the whole cup. And the trick is to do it fast enough to make a difference, but not too fast. So 1, 2, 3. And I'm not sure if Math Dad has tried this recently. So I'm going to invite Math Dad to come behind our table real quick, because I have a second plate. And let's see if he can do it as well.
All right.
And here's your egg.
All right. I'm going to try to knock it forward here.
Here's my egg. All right, we'll try and go forward. 1, 2, 3. Woohoo! And if you do not have plastic eggs that you can put Play-Doh in, you can do a real egg too, but I recommend hard boiling it first. Sometimes you'll see this done online where they use an egg that is not hard boiled and they have some water in the bottom. But if you don't get that force just right and your egg falls off onto the table, it will crack and make a mess. Hard boil it first, and then you'll be good to go. Now watch what happens if instead of, let's say you don't have a pie plate, you don't have an egg or a cup. Well, you can use other things too. So instead of using an egg, I'm going to use a bunny. And instead of using an aluminum pan, I'm going to use a paper plate. I cut the edge off this paper plate, and then I tied a little ribbon on one end. And now let's see what happens if we stick our bunny right here. In fact, should we do a double bunny drop? Let's do a double bunny drop. All right. Think I can do it all by myself? We'll see if I pull fast.
3, 2, 1, go.
And the bunnies land in the cups if we pull out fast. But what if we pull out slowly? If I put this bunny back on the plate and then I pull slowly, it does not land in the cup. Because there is friction And if I'm sliding it out slowly, the bunny is just going to stay on that plate and then eventually fall off. You may have seen the tablecloth trick of putting a tablecloth down underneath dishes, and then if you pull really fast, it will come off and the dishes will stay in place. That's actually a pretty tricky one to do well. You have to have a very smooth tablecloth, and then the things on the table have to be of the right weight, because if they're too light, they'll fly off, and if they're too heavy, sometimes there'll be enough friction that they'll actually move more than if they're kind of in just the middle weight of being just right.
So I'm curious, if this weighs a bit, it's not terribly light.
Mm-hmm.
Is that important?
Yes, let's try something really light like a cup. And here you'll see that speed makes a big difference. So if I pull pretty fast, ooh, it works. But if I pull just a little bit slower, put this up here again. I'm too good. It worked again. Oftentimes, if something is really light and you pull a little slower, it won't work. And the best way I can show you that is to set up two towers. We're going to do one with blocks, which are fairly heavy, and one with cups. And then we'll see which one is easier to do. And you can use any type of paper here. I've got index cards that I've just put a little bit of duct tape on, then punched a hole and attached ribbon to. And we can make our stack of cups here like this. And if we pull fast enough, our cups should make a stack. But our cups are really light, so this is going to be much more challenging than if we did the same thing with blocks. So over here, we've got some wooden blocks that are fairly heavy. We'll do one and then another, and then another, and another. So we have 3 wooden blocks, 3 cups. I'm going to give Math Dad the more challenging one of the cups. So come on over and let's. So you start at the top. Start at the top, grab onto your ribbon, and then 1, 2, 3.
Oh, so close.
And then the next one. You can see how high you can get your cup stack, because the taller it is, the more challenging it is, because when you pull those cards out, they'll drop and stack, but each time they drop, they move a bit. And I've never been able to successfully do one more than 5 cups high. So if you do 6 cups and it works, post about it online and tag me. I want to see it, because it's really challenging to do more than 5 cups. I will come back over here, and I'm going to take just a quick minute to see if there are any questions about inertia. I see someone asks, can you use toys? You definitely can, especially the one where we did the bunny drop. You can use any type of toy for that. Anything that will fit inside the cup will work. And those bunnies do weigh the same amount. Oh, what else can you stack? That is a great question. You could make your stack out of pretty much anything. Whoops. I keep accidentally clicking on the wrong ones because they're moving so fast. I do like Bill Nye the Science Guy. And another question that I asked is, can you do 10 cups? I have never successfully done 10 cups. The highest amount that I have done is 5, but you can use any type of cup that you would like. Could you use books? That's a great question. You could definitely use books if you don't have wooden blocks. The books, because they are longer and wider, they would stay really well. It would not be very easy to pull too slow and have them come off. And how light can an object be? A ping pong ball is really light. So our egg drop that we did, if you have a ping pong ball, that's a little trickier. It will usually fly off with the object because it is so light. But everything else I've works pretty well. Can a car or object that is big do the same thing? That is a great question. The bigger an object is, the more inertia it has. And so to demonstrate this, I'd like to ask Math Dad to come over here real fast.
Okay.
So we took Taekwondo together a while, and if he, let's see if I can do this standing here. So if I lift up and I try and sidekick him, he's got a lot of inertia because he's way bigger than I am, and it takes a lot of force for me to move him. But if he, very gently please, reaches up he can move me a lot more easily because I'm lighter. The bigger something is, the more inertia it has. And so something as big as a car is so heavy that if you tried to do some sort of a stack with a car and paper in between, the paper would just rip and come out, and your cars would not move at all because they are so heavy. They have so much more inertia. The more inertia something has, the more difficult it is to change its motion. And that applies to both cases. So inertia of being at rest, if a car is stopped, it takes a lot of force if you're going to try and push and move it. And if something is moving, like a planet in orbit, it's not going to stop easily. It's not going to stop easily. It's going to take a lot of force to get it to stop. I'm going to ask just one or two more questions. And then can you, what about clay bricks? You could definitely use clay bricks. You can use lots of different objects. So quick little recap of inertia, different things that you can do with inertia. The egg drop, you could use anything that is flat. And then for your object, if you want to have it fall and it's smaller and lighter, if you put that toilet paper tube in between, that just sort of helps to get that plate out of the way. But like you saw with our bunny drop, you don't even have to use a toilet paper tube. You can just use a flat piece of paper or cardboard and then pull out and have whatever toy or other object you have land inside the cup. It's quite a bit of fun. Now I'm going to have Math Dad share just a couple more of our drawing submissions with you because I have a little bonus experiment that I'm going to grab that we're going to do in just a minute.
Okay, where are we at?
Right there.
All right, here we have a bit of a playground. My screen's actually so small I can't read this one, but this guy actually wrote, whoever did this, wrote a little poem to go along with it, and I thought it was super cute. You kids have amazed me with the stuff that you've been able to draw, and also some drawing skills. Oh, here we see a view from the window. You guys live somewhere more exotic than I do.
This one was made in a drawing program, and they have a lot of hawks that they see outside their window, and instead of a hawk, they drew a phoenix. Isn't that great?
Ah.
Isn't that great? I love that one.
I love it.
And then this one, if I looked out the window, I would see pirates having a party on a boat, and then I would go join them. I loved that one. I would definitely go join pirates too if I saw pirates having a party outside my window. One of my favorite science demonstrations that I do is about the Bernoulli principle, but because it uses a hairdryer and it's pretty loud, I didn't think that it was a good fit for live streaming, but I do want to show you one simple thing that you can do with it because it is such a fun demonstration. But first, I'm going to turn around to the whiteboard and explain a little bit about how the Bernoulli system works. And then I'm going to show you how you can have some amazing fun with just ping pong balls and a blow dryer. And if you don't have ping pong balls, you could get a balloon and just put a Skittle in it or two, and it would work rather well. And I'm going to ask Math Dad if you could kind of turn on this light because we're a little bit dark over here. Now, Bernoulli was a scientist who lived several hundred years ago, and he was the first person to describe this. And he said, if you increase the velocity, then the pressure will drop. Now, those are some big science words. What does velocity mean? One of my favorite ways to remember what velocity means is to think about how it sounds a little bit like velociraptor. A velociraptor is a dinosaur I love, but would not want to meet in real life. And so you can get your little velociraptor claws ready and say velocity means speed. The faster something moves, the more velocity it has. And if air goes faster, then the pressure drops. And that acts like suction and pulls on all sides. And to show you just how cool this is, I'm going to get ping pong balls and a balloon. And then if you can get a balloon and put a Skittle in it or two, then it will have just the right weight to do some really cool tricks with a hairdryer. So we're going to come back over here and grab my ping pong ball.
I have no idea.
And then I'm going to take just a minute for Matt to find a balloon, which is in the Epic Electric box right down here. And then you can put a penny in the balloon if you don't have a Skittle. And that's something you can use just in case you don't have a ping pong ball. So check this out. If we turn on if I toss a ping pong ball up and catch it, gravity brings it down, and then what's sending it up is the force of my hand. But if we have air, a stream of air, instead of my hand pushing it up, check out what happens. It hovers in place. And you might think it's hovering in place because those forces are balanced. Air pushing up is the same as gravity pulling down. But if I turn it to the side, you can see that way more is going on here than just air pushing up and gravity pulling down, and that something is the Bernoulli principle. And the way the Bernoulli principle works is that because our ball is round, we have forces on either side that are pulling, and they're balanced, and so the ball is going to stay. If you take a ping pong ball that has been stepped on and is flat on one side and try and float it, it will just fall right off, and it will not stay because those forces are not balanced. You don't have even pressure on both sides pulling up and down the same way. And now I need to give a little.
No, so you've got lots of good stuff with this demo. We've got to save the good stuff for another time because this demo is just too good. So think of this as a spoiler.
A spoiler alert.
Yeah. So, yeah, or at some point in the near future, because there's some good ones to go along with this that we don't have ready.
Quite yet. That's right. We can't find balloons. So, and then last part of our inertia demo is inertia beads. So these are made out of party necklaces. I just took party necklaces and then I took duct tape, I cut them apart, took duct tape and taped them together. So this was a party necklace. Then I cut it in half, put a little duct tape on the one end to join these two together, and then we connected them into a big, long strand and put them in a jar. And now, do you want to be the one to give it a pull? If you get the beads started.
Can I see? Do we want a white background?
Oh, maybe we should do the white background. Now, if you get the beads started, they will jump right out of the cup all on their own. That was kind of crazy. And from my point of view, it looked like you couldn't even see the silver beads because the way that the light was reflecting. So it was like the beads disappeared for a half second. So those are inertia beads. You can make your own if you have party necklaces. And the reason that they work is because the beads are connected, they're spaced regularly. And when 3 of them kind of kick up at the same time, that transfers some energy to the next little set of 3 beads, and they transfer energy to the next set, and then they get going and get going and get going. My advice for putting them back in is to put them back in the same way that they came out. So if you just scoop them up like this, like a big handful of beads, and then you shove them in the cup, they're not going to jump back out for you. You've got to put them in bit by bit. So you start with the one end, and then you just put them in little bit by little bit. And when you're doing this, it's a good idea to have the cup on the floor, because then if the beads start to get away from you, they're not going to do it quite as fast. Once that little edge of the beads gets below the cup, that's when they really start to speed up. So if the cup is on the floor, that one edge isn't going to get below the bottom of the cup, and then they're not going to go too fast. So that's my little tip for doing those inertia beads. I'm going to check real quick. We will do more with the blow dryer a little bit later. Yep, like and Math Dev is right. I wanted to give you kind of a sneak, do that lesson real quick, but he's like, no, you've got so much stuff with that demonstration, we should save it and have it be its own thing. We are going to go to fact or fiction now. And if you printed out our little handout, then you have the fact or fiction facts already, and you may have even had time to look them up and know about them. So Math Dad has not seen these yet. I'm going to ask him our fact or fiction facts and see how well he does. So our first fact, and you have to tell me if it's true or false, fact or fiction.
Oh, you said it's a fact. I think it's a fact.
Our first statement is peanuts grow on trees. Is that true or false? Peanuts grow on trees.
They grow at the grocery store, don't they?
They do not grow at the grocery store. No.
Peanuts grow on trees. I think it's true. They've got to grow on trees. They're nuts. Nuts grow on trees. Are they nuts? I don't know.
A lot of nuts do grow on trees, but peanuts do not. Peanuts are actually in the legume family, the same type of plants as beans. And here's the crazy thing about peanuts. They develop underground. I kid you not. This is the coolest thing. Peanuts are one of the most bizarre plants. So the peanut plant flowers, sends out these flowers, and then once the flowers have been pollinated, they actually dive and like bury themselves underground, and the peanut forms in the dirt. And if you want to help your peanuts form better, in peanut farms, they'll actually kind of pile up the dirt around the plant as soon as it finishes flowering to kind of help those peanuts get in that nice dark environment. And that's how a peanut grows.
So is a peanut a nut then?
It all depends on how you define nut. If you define nut as being a hard, and the general definition of nut, I looked this up yesterday, is actually very vague. It just says like a fleshy thing you can eat inside a hard casing. So by that definition, a whole lot of things are nuts. But they are not tree nuts. Peanuts are not on trees.
All right, you got that one.
All right, you ready for fact number 2?
Yeah, okay, I'm warmed up now.
Statement number 2. Okay, and I have to say, in the chat, you guys were on the ball. You really knew about peanuts. I saw a lot of false for peanuts
grow
growing
on elephants. Trees. Somebody said so.
Peanuts grow on elephants. I love it. Statement number 2: caffeine is a natural pesticide for the coffee plant.
Okay, so coffee plants, I'm sure they've got caffeine in them. Pesticide. So like insects would not like eating it because caffeine would make them all jittery or whatever caffeine does to insects.
Exactly. So
it sounds totally plausible. True.
It is true. It is true. Caffeine is a stimulant, and for us, we like plants like coffee or chocolate that produce caffeine because it helps us to be a little more alert. It's a stimulant and increases your heart rate. But for an insect, think about how small an insect is compared to a person. If an insect starts eating the coffee plant, it's like, ooh, heart attack. The caffeine is just way too much. And so that's actually the purpose that caffeine serves in plants that, like tea and coffee that produce caffeine. It serves to protect them from insects that would eat them. Pretty cool fact. And do you know who else cannot eat caffeine? So insects can't tolerate caffeine.
Is it dogs?
Yes. Caffeine is poisonous to dogs. So that's why you're not supposed to feed your dog chocolate, and you should never give your dog coffee or anything like that because caffeine is poisonous to dogs.
What about other animals?
I don't know. I've never researched about other animals. Something to look up.
Interesting.
You ready for our third fact or fiction?
Ready.
Elephant grass is so tall an elephant can hide in it.
Is elephant grass even a thing? You're making this up.
Elephant grass is a thing. There's
okay.
a grass in Africa called elephant grass.
All right. Well, I've seen really tall grasses where like lions hide and wave, but there's no grass tall enough for an elephant. Okay, false.
True. I did not specify the size of the elephant. Elephant grass grows up to 10 feet tall. I mean, that's as tall as our ceiling. That's really tall. And do you have elephants taller than that? Maybe, but most elephants can hide in elephant grass. It's that big.
Dang.
Pretty cool.
Yeah. All right, 1 out of 3. Okay, I'm not winning today.
And then the last one, there are no blood moons, no solar eclipses. If there's a lunar eclipse, we call that a blood moon because the moon looks red. There are no blood moons in the year 2020.
Oh, no. So it's just specific to this year.
Specific to this year. And this year, are you going to see a blood moon? Will there be a blood moon? Our statement is no. There's no lunar eclipse in the year 2020.
Okay, so no, that's false. There has to be. I think there's got to be one every year. They're more common, the lunar eclipses.
I got you. And I'm kind of secretly pleased by that because this is a statement in our little calendar. Do you remember this?
That I was supposed to have proofread?
Yes, that you were supposed to have proofread. So we have, and I'm going to ask one of the science moms to drop a link. You can get a free PDF copy at our website of this calendar, but in the back, it shows you that in the year 2020, there is only a penumbral eclipse. That's when the moon is sort of in this like extra part of the shadow where it's not a complete shadow of the Earth. And so there is no full lunar eclipse this year, only penumbral eclipses. And penumbral eclipses are so subtle, they're really hard to see. You really need a telescope to appreciate what's going on. Otherwise, it just looks like maybe there's a very thin cloud in front of the moon. It looks like the moon's not quite as bright, but there's no color change at all. So
that's interesting. But the lunar eclipses are much more common than a solar eclipse.
Lunar eclipses are more common than a solar eclipse, and we have several penumbral eclipses. But because of the position of the moon, it usually works out that we either have multiple blood moons in a year, multiple lunar eclipses, or we just have penumbral lunar eclipses. It's usually one of the two. So if you see one lunar eclipse in a year where the moon turns red, chances are there will be another one. Or the next year, there might not be any. It just depends.
So with a solar eclipse, to really experience it, you had to be in a very specific location. With the lunar eclipses, I imagine you just have to be able to see the moon. Your location's not going to matter nearly as much. Is that
correct? Correct. Yeah, location's not going to be quite as important. All right, so that is our fact or fiction. And before we go over to our engineering challenge, which is the next part, I'm going to share just a couple more of your drawings because we absolutely loved seeing these fantastic views from outside my window. So let's see, did you do that one? The white Nancy one? This one had a fantastic, I hope you'll check it out on Facebook because there was a little poem with it that rhymed and said how many things were wacky. And I think there were 21. It was just outstanding. So tons of wacky things in this one. And again, on our Facebook page, you can check it out and see the little poem. And then this one I also thought was wonderful. There's a dragon and you can see the little playhouse they have in their backyard. And then we'll do one joke and we will get our challenge set up. So our joke is, what do you call a dinosaur that crashes his car?
What do you call a dinosaur that crashes his car? Crashosaurus?
I actually don't remember. Do you remember?
I don't know. I didn't write these answers. Uh-oh. Does somebody at home know?
Science Mom Krista, help us out. We forgot. It goes through a jarring experience. That has to be what it is. No, that's not it.
That was yesterday's. Oh, there it is. Tyrannosaurus Rex. WRECKS.
Oh, that's so good. Tyrannosaurus Rex. We're keeping it real today, guys. You can tell with like 3 days, we're starting to be like, whoa, this is. But we are super excited for today's engineering challenge. Today's engineering challenge is to build a boat out of Legos and then see how much weight it can hold before it sinks. And if you do not have any Legos, fear not, you can make your boat out of any material, any type of material that you want. And then you just need to find some objects that you can fill it with. When I was looking around our house this morning, I actually did not see enough coins. We didn't have enough coins to put on the boat to make the weight. So I was like, oh, pennies is not going to work. But I found this bananagrams game. Aha, perfect. And I thought, you know what, with bananagrams tiles, those are kind of heavy. There are lots of them. We can definitely use those to make our boats sink. And then I counted out Legos, and there are equal Legos in each of these. And my question for Math Dad is, do you want to be the sort of excited Unikitty that has a stars in her eyes, or do you want to be the calm Unikitty who lost her horn and instead has flowers?
All right.
All right, I'm the flower Unikitty. Math Dad is the regular Unikitty. We're going to build our boats, and then we'll bring you guys a little closer so that we can have you guys see exactly how much material they hold before they sink. And if you're watching at home, now is a great time for you to build a boat as well. And again, if you don't have Legos, not to worry. You can use any type of material that you want.
Maybe you got some Play-Doh, maybe you got some clay.
Cardboard box.
Piece of paper. Try to fold one and decorate it out of a piece of paper. All right. So we're trying to make it so it will hold as much as possible.
As many bananagram tiles as possible. That's the challenge.
Okay.
And I did have my sister called me yesterday, and in the background, I could hear her daughter, my little niece, at the top of her lungs, singing, I'm singing a song, I don't know the words to this song.
She got it wrong.
Oh, no.
Okay. I'm singing a song, I don't know the words. I don't know the words to this song. I'm singing it loud and I'm singing it long, but I don't know the words to this song. No, I don't know the words to this song.
That's how you do it.
That's right. It's my good luck song.
You're going to need it.
Oh, bring it on. Bring it on. Man.
And I guess we should have said in our little challenge we have here between the two of us, do you need to use all your blocks, or should we say no, you don't need to use all your blocks?
No, it sounds optional to me. Yeah, we don't want to.
You can use as many blocks as you want. And
oh man, it's gonna tip over. Oh.
And I think you should tell a story again.
Okay, so I've got another story that my kids love to hear. It has to do with when I lived on worked on my grandpa's farm. So we would milk the cows every morning at 3 o'clock in the morning. We'd get up, maybe about 4 o'clock when we actually started milking them. But we had 2 herds, and we would have to switch from one herd to the next. And after we were done milking them. And we had this cow on our farm, number 701. She was the smallest cow in the entire herd, but also she was probably the meanest cow. And one day she had this grub in her back. So like literally some grub that was
It's the larva of a fly. This is really kind of gross. They lay their eggs in the skin of these cows, and then they like develop, and then they'll hatch out, and when they hatch out it's really painful. It's like a big sore.
Yeah. And my brother squeezed the grubs out of her back, so kind of like popping his it. At any rate, you can imagine she didn't like that very much, and so he had done that the day before. Well, the next morning she was not in a very good mood. And I talked my brother into letting me go change the herd and get the second string of cows. And I usually didn't get to. So I left him in the barn. The very last one in was number 701. And she kicked my brother. First chance she got. He went under to try to get her cleaned up so he could milk her. She kicked him. Well, my brother wasn't going to take that, so he just punches her back. Well, she kicks him even harder the next time he tries. So my brother, being my brother, grabs this metal clamp and whacks her. Well, of course, she didn't like that, and she kicked even harder. Only this time, she kicked backwards and hit this metal plate, and it hurt her. And that made her angrier again. So then she just starts kicking harder and harder, and she kind of tore up the back of her leg. It felt really bad for her.
And I want to tell all the kids, 701 was okay. She comes out of the story being just fine. Still a cranky cow. But
that's right.
Just fine.
It's still not a favorite. Okay, so at this point, she's getting angry as can be, and Jeff can't do anything. My older brother, and so he just has to let her do her thing, and she lets out the beller of death. Never heard anything like it before or since, and so I'm about to close the gate on the first string of cows, and we hear the sound. Every cow in the barn goes, and then they charge. They come charging at me. I managed to get out of the way, just barely, and the cows are going right past. I'm getting manure flung all over me. Not very fun, of course, as you can imagine. And the cows go up, and they're bunched up against the barn. I've never seen anything like it. Obviously, they communicated somehow, and I slowly kind of make my way around, covered in manure, and I get back to the barn. What happened? And I was in a daze, and we talked about it, but we could not milk 701 that morning. we just had to let her go, and it took a few minutes to get the cows settled out, but I'll never forget that. So 701 and the beller of death. what we call that story.
That's one of our kids' favorites. They ask to hear it all the time.
That's right. All right, are we done?
My boat is ready.
All right.
I'm really curious to see how many tiles it can take. Your Unikitty has to be on your boat because this is the Unikitty's boat.
Of course, Captain Unikitty.
And I would love to hear you guys in the chat guess how many tiles we'll be able to put in before it sinks. So take a minute and put a guess in. We've got our tiles here. Do you think we'll be able to put in 1 tile, 5 tiles, 10 tiles?
Man.
I'm seeing, 20, 18. I'm seeing a lot of guesses.
You guys have way more. I don't know if it'll even float.
I tested mine out twice, and it floats okay, but not super great. We're pretty close to the waterline, so I'm not sure how long it's going to last. All right, so I've got, and we should say, so Math Dad used all of his blocks except for 3, and we have the same number of blocks to start out with. I used all of mine except for 6, and now we're going to put our boats in.
Let's do just one at a time.
No, we're going to put them both in at the same time, and then we're going to start adding our material. All right.
Yes, okay,
our boats are floating, and we'll do it at the same time.
Oh, it's filling up with water. Better hurry.
1, 2, 3, 4.
Oh no.
5. Math Dad sinks. Flower Unikitty for the win. My boat's still, look at that. I'm still floating. 6, 7, 8. I'm so impressed. 9, 10, and there we go. With 10, my boat is pretty much submerged. So 10 blocks for me. How many was yours again?
It was maybe a little less than 10. Okay.
Now here's the fun thing about this engineering challenge. After you do it and your boat sinks, you can take it out and then redesign your boat and try again and see if with a slightly different design, you have better results.
Yeah, it's filling up with water too fast. I'm not.
So
not sure.
Instead of, let's see, you did a similar design to me with going around the outside. That's what I did too. I also put ones on the bottom for extra stability. I don't know if that helped.
Yeah. So somehow they're getting a little bit loose. I didn't braid them in very well, so I'm doing something of a tie layer in there. But
you want to do one more test, and we'll see.
Ooh, okay. This one, water's coming in more slowly, although it's really lopsided. Oh my goodness, Unikitty, come on, throw your weight the other direction.
All right, I've got my boat here, and I'm gonna try again, and I'm gonna see if I can get 10 tiles on the second time. And this is a cool thing about science. If you do an experiment, most scientists don't just take their first result and count that. They like to repeat the experiment and see if they get the same results. And that's a great thing to do when you're doing science.
5, 6, 7, 8, 9. Oh.
I don't think it counts if your ship's already sinking. Oh, 10. It looks like 10 is the max. So if you build a boat and you get more than 10 bananagram tiles or more than 10 pennies, whatever weight you're using, post a little picture of your boat online. Use the hashtag Science Mom Squad. We'd love to see your creations.
So if they built the boat out of paper, would it work? If they tried to float it?
Paper boats will float, but it depends on how absorbent the paper is. They'll get soggy eventually and sink. The side of a cereal box will work better than paper if you're going to build a boat, and I would recommend putting duct tape around it because duct tape is fairly waterproof. So if you make a boat out of a cereal box, it'll be a little sturdier. You can put duct tape all around the bottom part, and then it should float pretty well.
Okay, well, that makes a lot of sense. Photo paper?
Photo paper might be less water resistance, but it still isn't going to be as easy to duct tape as cardboard. So I would recommend
cardboard box duct tape and duct tape with photo paper.
Can I just say that duct tape is like the best material ever? I love duct tape.
It is pretty impressive.
So quick story. I fought forest fires during in between college when I was going to college. That's how I paid for myself to go to college. Was in the summer I would work for the Forest Service. And then if I got called out on a few fires to go fight forest fires, that paid really well. And one fire I was on, when you fight forest fires, you're either really, really busy or you're bored out of your mind, one of the two. And one fire I went on, we had a lot of bored out of our mind time where we were just sitting and waiting and there was nothing to do. And I had a roll of duct tape. That roll of duct tape kept me entertained the whole time. I made a book out of the roll of duct tape. I made a wallet out of the roll of duct tape. I made so many things, and it was a lot of fun. Duct tape's amazing. Now, before we get onto our Minecraft mystery, I want to ask if anyone has any questions about the engineering challenge. We'll check the chat real fast for questions. And then Math Dad has another Minecraft mystery. And I will say, we haven't had time to respond to our email. Our inbox has sort of been overwhelmed. But I do want to thank those of you who sent in answers to yesterday's about how many, that question about Gauss. And if you were adding the numbers from 1 all the way to 100, what would the answer be? We had several people send in solutions. Some were correct, some were close to correct. And it was really cool to see that you guys were taking that extra step and trying to solve it on your own. We loved that. And here is our math mystery for today. We're going to be looking at drawing mazes. And while Math Dad is getting things set up over there, I'll tell you a funny story about how I got in a little bit of trouble yesterday. Because we have a switch that our kids like to play Minecraft on. And if our kids get the switch, and then they're using it when they're not supposed to, like they, take it out and sneak it into their bedroom at night to play extra games, then I take the switch and I hide it so that then they can't find it and they don't have it for several days. Well, yesterday, Math Dad wanted our son to build a maze in Minecraft so he could take a picture of it to share with you guys. And I had hid the switch, but I forgot where I hid it. It was such a good hiding spot that I couldn't find it. And so we spent about an hour yesterday looking for the switch. I finally did find it. And close the door here. Because my kids are not watching this right now, and I don't think they will go back and watch it, I'm going to tell you where I hid the switch, because it is the best hiding spot ever. And when I finally found it, I said, aha, this hiding spot's genius. I'm going to definitely use it again. You ready? It was not in my closet. Hiding it in a parent's closet is a really good hiding spot. A lot of parents do that. It was in the glove box of our car. So you open up the little glove box in the car, that's where I hid the switch, because I knew the kids would never look in there. But the problem was that I forgot that's where I hid it. So we took a while for us to find it yesterday.
That's evil.
But now Math Dad knows that that's where it was. So next time, if I hide it, we'll have a better chance of finding it soon.
We cleaned the whole house looking for that thing. That was what the real plot was. Science Mom wanted us to clean the house. Yep. All right, so last time we had a question involving young Carl Friedrich Gauss. And he was asked by his teacher to add up the numbers 1 through 100. And he was able to do it in just a few seconds. And he delivered his answer, and the teacher was dumbfounded. Oh my goodness, how in the world did he come up with the right answer? All right, so let's see if we can figure out how he might have done that. So I'll get to the Minecraft version of the question, that framing in just a moment. But I'm just going to write down these numbers. I'm going to start writing. So we had 100, 99, there was a 98, a 97, a 96, and this is going to keep going all the way down until maybe we get down to 51, 50. All right, and then I'm going to start on my way back up. 49, 48, all the way up down to 4, 3, 2, 1. So I've just kind of changed the orders of these numbers. And I want you to notice something. This is 100. These two together make 100. These two make 100. These two make 100. These two make 100. I've paired them up so that they're going to come in pairs. So I see here I have 49 different pairs. 1, 2, 3, 4, all the way up to 49 here, all of which add up to 100. There's another 100 there, plus 50 more. So altogether, that was, looks like 50 100s. So 50 times 100, we just add 2 more zeros there, 50 times 100, plus the 50 more. So all together, we get an answer of 5,050. So if you were able to come up with this answer, you did an amazing job.
Woohoo!
Yeah. And my guess is none of us actually just took the time to add up all those numbers. It's a lot of work. I don't think I've ever added up something that big in my whole life. So I'd be really impressed if you managed to do it.
Can I tell you a really fast story about counting to big numbers? So our oldest son really takes after Math Dad. And when he was 3 years old, he kept asking me to count to 1,000. And I was like, dude, I don't want to count to 1,000. That's going to take forever. And so I tried to put him off, like, well, how about we count to 1,000 by tens? And we'd do that and it wouldn't take too long. But then he was like, no, I really want you to count to 1,000 the whole way. And so finally, when we were driving somewhere and it was about a 20-minute drive, I said, okay, I'll count to 1,000. I started counting. And every now and then I would pause and say, do you want me to keep going? And he'd say, yeah, keep going, Mom. And we got all the way up to 999, 1,000. And he had a water bottle that had little markings for how many liters it was. It was 1,000 liter, 1,000 milliliter water bottle. And when I said 1,000, he held up the bottle and said, milliliters. He'd been tracking along the whole time, which I just thought was hilarious. But guess how long it took me to count to 1,000? Like 24 minutes. Yeah, takes a long time.
Yes, indeed. And in the grand scheme of things, 1,000 is not that big of a number. The numbers go way past that. And we could have asked instead, add up all the numbers from 1 to 1,000, 1 to 10,000, 1 to 1,000,000. And that would have been a perfectly reasonable question. And you definitely wouldn't want to try something like that by hand. All right, so just a reminder about what we did last time. We set up a table of values. N was the number of terms we were adding. So we'd reframed this question. We were doing 1 plus 2 plus 3 plus 4. So adding up these columns. And we said, all right, suppose we had a tower of height n. In that case, how many would there be? A staircase, I believe we called this. So thinking about building this in Minecraft. And we wanted to try to figure out what was the general pattern here. So there was just a 1-by-1 staircase. It's kind of boring. G of n was our notation that we used for the total number of blocks in our staircase. That was 1. All right, then when n is 2, we had 3 blocks. When n was 3, we had 6 blocks. When n was 4, there were 10. When n was 5, there were actually 15. And then here, I've actually drawn one that's 6 tall. So if we count all of those, we're going to get 21. All right, so if there are 21 here, all right, what's the pattern? What if there were n blocks? In that case, how could we possibly count this? And there are lots of good approaches here, but the approach that I'm going to suggest by grabbing a different color marker here is to redistribute these. So I'm going to take these blocks here, and I'm going to take them, turn them over, and I'm going to add them right here. So what size is this new region going to be? So cross those ones off. Well, originally there were n, so now there's one more. I'm going to call that n plus 1. And it's okay if you're not able to understand this. So these variables are new to you. This is not something you've used before, but I know so definitely some of the older kids are going to understand this. All right. Now, what about the height of this size, of this side right here? Well, I basically just cut this vertical side in half. So I'm going to end up with times half of n. So, or n divided by 2. And this formula will work for any number n. So when n is 100, in that case, I should do, according to this formula, 101 times 100 divided by 2. And if you multiply that out, 101 times 100 divided by 2, you'll get 5,050, which is the exact answer we said we would get before. And the beauty of having a formula like this is Now we haven't answered just one question. We have answered every version of this question. We know the number of blocks that will be in this staircase. If I want to plug in n equals 10, I can get my answer. If I want to plug in n equals 1,000,000, I can get the answer there. So it's so cool that by coming up with a formula, or this is what we call modeling with algebra, we are able to answer all the staircase questions of this type, where we've only answered staircases that always go up one over one, up one over one. There are lots of different types of staircases that we can get, and this is definitely just a two-dimensional version, but we have solved it completely.
That is really cool that now you have it answered for every single case.
That's
I love
right.
that.
All right, so that was our math problem from last time. Today, we're going to do one of a very different flavor. So I'm going to pull up the work that my son had done. So the challenge problem for today is going to involve solving this maze. And if you look at this, this actually doesn't look like a very hard maze. We are trying to enter here at the bottom left of this maze, and then we're trying to navigate up to that beacon that's at the top right of the maze. And you can see there are going to be lots of different paths that will get there. So it's not a question about can you find that beacon. Instead, today's question is going to be about how many paths will lead to that beacon. And the answer there is there are infinitely many paths, because you could go in as many circles as you want to get there. So we're going to restrict the rules. How many paths would lead to that beacon if you are only allowed to travel to the right or to travel upward? And before we can get to this question, we need to learn how to answer slightly easier questions. So here's a different version. This one will actually have even more solutions because there are more possible ways to turn right or left. And then here is an even easier version of us trying to get up to the beacon. So I'm going to go back to the board, and we're going to see if we can draw out what's going on here.
We've had a bunch of kids who said they'd like a little more explanation of the math problem. So just giving you a heads up that that's in the chat. We might want to circle back at the end, just a little more. But I think we'll do the maze first.
Okay, yeah, we will plan to circle back. So the more specific the question, the more specific my answer can be. But yeah, it is easy to go really fast on something like this, especially when you've learned it many times and you know it really well. Sometimes it's harder to explain something that you understand well. But there's no better way to learn something than to try to teach it to someone else. So I really like that you're asking questions, and I hope you do that in your school classes. If you don't understand something, don't wait for someone else to ask the question. Just raise your hand and say, teacher, can you please explain that? And if you can explain what your reasoning is and say, I don't understand that. I would have tried this, but you're saying we should do this, and then see what type of answer you get. Teachers love it when students ask their questions, but so many students are maybe afraid to ask. They wait and think, oh, everybody else must understand it. I don't understand it. But in truth, everybody's just sitting there waiting for someone else to answer. And so we appreciate it as teachers when you ask good questions. All right, so back to our maze challenge. So in this case, we had something like this. We've got maze border, and then 1, 2. I'm just going to look at that very easiest of cases. All right, so we're trying to get to this star position, and we are starting right here.
So we're trying to get to the beacon.
So we need to get to this beacon. And first of all, let me ask Science Mom, do you know how to do this?
No. I don't actually.
Yeah. So
if I were trying to do this, I would just draw out paths with different colored pens or markers and then try and be like, did I get them all?
Okay, well, and you know what? I think that this one might be easy enough that we could draw every possible path, because I picked one that was small, although That's still going to be a lot of paths, because I mean we could go over, up, over, up, up. We could go right, up, right, or up, right. And boy, trying to keep track of all that could be really tricky. But just in saying that, though, we've kind of framed the question in a way that we can answer it. So what if I just started writing out a letter for my direction? So I would use U for up, R for right. And so in that case, if I went up, right, I might call that path U, R, R, R.
Ooh.
Ooh. Or if I went right up, I would write R, U, R, U, R, U.
Are you always going to have 6 movements to get there, no matter what path you take?
Was that a joke? Are you always going to? Because it sounds like a question. Are you?
No, I'm serious. All right.
Oh, okay. But
are there always going to be 6 movements?
Okay, excellent question. Will there always be 6 movements to get to this star? For this particular map, yes.
Ooh.
But not for all maps. And that's where it's going to get really tricky. But I like what you're asking. But what we've done in writing this out, and once we realize that there are always going to be 6 decisions to make to get to the star for this particular map, then we could reframe this question about the number of paths as a question about how many ways can I write a word using U's and R's. And the answer to those 2 questions will be the same number. So we are kind of diving into a math of branch called combinatorics, which is all about counting things. And there are good methods for doing this. And I'm not going to pursue them too far, but there's actually a nice formula for choosing the number of ways you can choose 3 locations for the R's out of 6 objects. So if you've done combinatorics before, this would be 6 choose 3. So, but I'm actually not going to follow this line any further, just because we're going to deal with some maps that are where the problem is different. There might not be 6 paths always, or 6 decisions to make to get there. 6 directions to choose. All right. So instead, what we're going to do is I'm going to try to just locate where were all the points where we had to make those decisions. And so, yeah, why were there exactly 6? Let's see if we can figure this out. So I would start here, and then no matter what, to get to the star, I would have to move over 1, 2, 3. So there will always be 3 moves to the right, and there will always be 1, 2, 3 moves upward. So
that's why there's going to be 6 movements total to get to the star.
That's right.
You have to move 3 sideways, and you have to move 3 upwards if you're going to get to the beacon.
That's right. So in that case, yeah, we just have to decide whether we're going to go right or up at each junction. Okay. So where were the other decisions going to be made? So right here, right here, right here. All right, and then we've finally made it. So I'm just putting a dot at all of these intersections, and then I'm going to maybe connect those dots with lines. And we're going to get a structure that we call a graph in math, so graph theory. Kind of fun. All right.
Someone just put in your song in one of the comments. I thought that was cute. Kind of funny.
Oh, you guys like my song? All right. I'm going to take this graph now, and I'm going to draw it a little bit bigger underneath. So I'm going to put a circle, 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 circle. Just going to repeat that. And then I'm going to connect the pieces. All right, so we need to keep track somehow of all the paths. And to do that, we're going to label it with some numbers. So this graph that I'm building, I've tried to build these circles big enough so I can write a number inside them, because we're going to do some bookkeeping. We're going to be accountants here. And what I ought to be doing is maybe even putting an arrow on each of these, because we've restricted our problem so that you can only go in one direction. along a line.
That's right. No going down and no going to the left.
That's right. You can't retrace
So
your route.
in our family, we call this the controller is old, because for a long time when we'd play Minecraft, we had a couple controllers that were broken and you could only move one direction. So that's kind of where we got the idea for this problem.
Okay, so how many ways can I end up here? Well, there's only one way. There's really only one way. So I'm putting a number 1 here. All right. How many ways can I reach this circle? Well, there's also only one path that led me there. Same thing with this circle here, one path. And for that matter, same thing along the whole bottom edge. There's only one path that would have led me to here. So I just take that. There's one. I look at what number came before, and I just transfer it. What number came before that one? A 1. Okay. Same thing is going on right here. There's only one way to get up 1. Only one way to get up 2, only one way to go straight up. So I put the number 1 in all of those. So nothing too exciting yet. But now, how many paths would lead me to this circle right here?
2 paths.
2 paths. Well done, Science Mom. So in particular, I'm looking at these numbers that came before, a 1 and a 1. I'm going to add those together, and that will give me the number of paths that led here. Aha. Okay. What about up to this guy? Well, there was one path from the left, but from below there were 2 paths for a grand total of 3 paths. Okay. And this top one here, there was 1 from the left, but 3 from below for a grand total of 4 paths. Okay. And similarly, 2 plus 1 is 3. And 1 plus 3 would give us 4. So I think things are kind of symmetric here. All right. How many paths would lead to this particular location? And I just add all of the pieces that go into that. So the 3 plus the 3. And that's going to give us 6. All right. To get over to here, 6 plus 4 is 10. 4 plus 6 is 10. And finally, how many will get us to the very end? The answer is 20. Slightly bigger box to even fit that number in. And that gives us our solution to this small Minecraft problem. All right. How would things change if we were looking at a bigger problem?
Can I say something really fast? Yeah. I love. First of all, I'm curious, Math Dad, do you know what you can do with a beacon in Minecraft?
Boy, I've seen lots of.
So they're like a big light that like goes up into the air, kind of like that huge light off the Luxor Casino in Las Vegas that we can see at night.
Usually my kids just make it like, come find me, Dad. I'm over here. Where? Yeah. I'm over here. Where? And
they're like, I made a beacon. Come get the beacon. If you're close to a beacon, you can get kind of special powers and things, similar to like what you can do with the potions. But what I love about this, the way that this is drawn out, is we've answered all the questions. So if your beacon is here instead of here, you know 6 moves. If it's there, you know 3 moves at most to get there.
Yeah, so if these are your cool. Final targets, where if you put the beacon there, yeah. That is cool. But of course, that only actually worked for this particular map. So what happens when we change what the map looks like? Well, in that case, we've got to redraw things and recalculate. And so, for example, if I draw a bigger one here, so put my border in, and then square, but maybe I put a rectangle there. Maybe put a rectangle there. Oh. So here, target that just a little bit higher to make sure you can see. Yeah, this would be a whole new question. So if my beacon is up here at the top right, so same rules, we're only allowed to travel to the right and up. In that case, what would we need to do differently? Well, we would have to draw a whole new graph. We would need to figure out where were the points where a decision could be made. And may be possible that there's not really a decision being made. Like, for example, at this point, there's not actually a decision to make, because I literally just have to go to the right from here. But I'm going to go ahead and add the point there just to make sure that I'm counting everything. All right, so we would take this graph, we would connect it with edges, and we could turn it down here. We would do the exact same thing. We'd put circles here, and we would try to just put the numbers in and count things from there.
And if you print out the handout, and I'll ask Science Mom Krista and Emily and Liza, one of them, to drop the link to this in the comments. But if you print out the handout, you've got a copy of this little map right here already drawn for you, and then you can draw on it to figure it out.
That's right. And so next time we will revisit that particular map, and we will reveal the answer to the question. But what I'm hoping you guys will do is you'll go home and you'll draw your own maps, and that you'll map it out. And let me just point out, so this one was kind of fun, but we could just make up any version of this on our own. So I can put a circle here and some other circles here, and I could just make up rules for where I can travel. And then we could count the number of paths that will lead anywhere.
Whoa.
So if I wanted to start here and try to end up here, it's kind of important that I don't make any loops in this, so that mostly I've been trying to head rightwards with the way I drew my graph here. Because if you could do a loop, then it's impossible to count all the possibilities. But for this particular graph, if I want to start here and end here, let's just fill in the numbers, see if we can do it. All right, so there's one way to get here. All right, that tells me then that I can't jump to here yet. I cannot fill this one in because there are two arrows, and I don't know the number that's in this other circle. So, but I do know the number of ways to get up here. There's one way. Ooh, that means 1 + 1 is, there's 2 ways to get here. 2 + 1, there are 3 ways to get there. All right. So there's only 1 way to get up there. All right, ooh, this one has 3 different arrows coming into it. So we would do 1 + 2 + 3. So in your Minecraft maze, I don't think that's going to happen at all. So there are 6 ways to get to this particular node, and then 6 + 1, there were 7. So there were 7 ways to go from from the start to the end for this particular maze. So while you guys are home today, draw out some mazes. See if you can find the number of ways to go from one end to the other. And yeah, so feel free to do it in Minecraft, but also feel free to just draw it out. And it's not a hard maze to solve. That we don't want you to draw a hard maze to solve for this particular problem. It's a different type of maze problem where you're just counting the number of paths that will take you from one end to the other. So good luck. I'm very excited to see what type of mazes you guys come up with. I do have one piece of advice for you. When you're doing your drawings and of any type, make sure you try to use dark colors. Some of the drawings are posted and they're in pencil and they're really light and hard to see, and then everybody can't appreciate how cool your artwork is. So you try to draw a little bit darker, or maybe if you did it in pencil, then you come back with a pen or something that's a little bit darker. So that's just my 2 cents on that.
All right, give a little claps for Math Dad. Thanks for the math lesson. And now it's time for what's in the bag. But before we do what's in the bag, we are going to share a few more pictures as well. I have seen a couple requests to share pictures of the leprechaun traps. We did make a little video that we were going to play at the beginning of yesterday's Quarantime with just a slideshow of all the leprechaun traps that we got, but that we had technical difficulties and weren't able to share it. That video is on the Facebook page, so you can watch it there. And I'll see if maybe at the end of one of our future shows, once we get that figured out, I'll include that video again, because they were fantastic leprechaun traps.
We can only show things that we've uploaded in advance here.
Yeah, and we're still sort of figuring this out. So another view outside my window that I wanted to share was this one with mixed up fruit. So it's a wacky view because all of the trees have different fruit than they're supposed to have. And then I love, just like in the Wacky Wednesday book, we've got a broken hose and then a few other things that are strange. And then this one I thought was, this is one of our leprechaun traps that I thought was real fun. Great leprechaun trap. Thanks for sending that in. And now it's time for what is in the bag. So I have clues. And if you printed out our little notes, you can see 3 of the clues. Math Dad has not heard any of the clues. So we're going to see if we can stump him on what is in the bag. I have ears and I'm covered in bumps. Those are the first 2 clues. I have ears and I'm covered in bumps.
Ears and I'm covered in bumps. So we have a pet lizard that might have bumps and ears. Did you have Delta?
Not a bearded dragon. No, Delta is not in the bag. It's not a bearded dragon.
Yeah. Okay.
Next clue, I can't hear. I have ears, I'm covered in bumps, but I can't hear.
Ears and bumps, and you cannot hear. You might have to help me out in the chat here.
All right, take a peek in the chat.
Frogs. Corn.
Yes, the answer is corn. So corn has ears of corn, but can't hear, covered in bumps, and then grow on a plant was going to be my next clue if you were having trouble. But I think it's more fun for you to look at in the chat. And so many of you got that right. Nice work. Good job.
That's why I keep them around, to help me out when I'm struggling.
That's right. And then we're going to change the format for the next bit just a little bit, because we've been getting some outstanding question. And as we keep going and kind of figure this out, I want to kind of collect some of the best questions and then answer and kind of prepare some fun little answers for that. One of the questions that we got was something that I had that I drew a comic about earlier. And the question was from Chloe, and she asked, why do some gases smell and others don't? So some things have a really strong smell, like natural gas, like with your stove, they put this sulfur-containing compound in it that has a really distinct smell, but other gases don't have a smell at all. And why is that? And it's because of receptors that you have in your nose. And there's certain things that a dog could smell that humans can't smell. It all depends on what little proteins you have in your nose that are designed to recognize a molecule. And they're so sensitive. Smell is just fascinating because there's certain smells that we're really attuned to where just 1 or 2 molecules will hit that little protein, and then your brain is like, I smell this one thing. Some things we need to get more of them before we can smell. It all depends on how many receptors we have. But one sort of funny one funny question is, why can some people smell that their pee stinks after they eat asparagus, but some people can't? And so this is what we're going to be exploring with this little comic. And I've got to give a shout out to Math Dad for this, because when we first were having a discussion about this, about why some people can smell asparagus pee and other people can't, Math Dad just sort of said offhand, what if, and kind of gave me this funny little anecdote. And I thought it was so funny that I made a comic about it. So here we go. We'll read this. So if you had a farmer several hundred years ago that found a magic lamp, he would say, what's this? And the genie comes out.
I will grant you one wish.
And he says, I can wish for anything? Now, other people might have wished for food or gold, but this farmer was a little eccentric, and he wanted something with more permanence. And he wishes to have the ability to smell something that no one else has ever smelled before, and for that trait to be inherited. And then, 900 years later,
everyone's pee smells after eating asparagus, but only certain people can smell it.
And this is a true fact. Everyone gets the stinky pee, but only a few people can smell it. And then this farmer in the next life is looking down and saying, I'm so proud. And the fellow angel says,
that your trait contaminated the gene pool?
And he says, no, I'm proud that they figured it out. And this is a true fact. Asparagus contains this amino acid called asparagic acid. And when your body breaks it down into sulfur compounds that contain sulfur and are small. And that means that they can kind of escape into the air and they're very fragrant. So these are the compounds that you get out into the air when you urinate after eating asparagus. And that's why it has the smell. And most people have what's called anosmia. That means kind of like amnesia means you don't have memories. Anosmia means that you can't smell these chemicals. Only, and it depends on the paper you read with how many people they estimate can smell them. But one estimate said between 20 and 40% of the population can smell this, and the other can't.
So it's less than half.
Yeah, so less than half the people can actually smell the smell. But the smell is fairly strong enough that in the 1800s, there was a sign in a little men's club in Britain that said during asparagus season, members were requested not to relieve themselves in the hat stand, which I thought was really funny because it implies that when it's not asparagus season, it's just fine to pee on the hat rack. And back in the days before we had indoor plumbing, I think people were a lot more cavalier about, stuff like that. So that was one great question that we got. And then another interesting question that we got was about hybrids. So if you have a hybrid, and when we did the mixed up animals, we saw such fantastic pictures of different animals where you take two animals and you mix them together. And if you get a hybrid, then we have sometimes kind of a special thing. And in plants, if you take two plants that are different and cross them, your hybrid will often be stronger and healthier than either of the parents. And so if you have, I'm going to do capital A for one plant and lowercase a for the other, the hybrid is this special plant. It has both from the capital A and the lower A, it got both, and that makes it special. And the question was, what if you have a hybrid with a hybrid? Is there a word for that? And there is not a special word for hybrid crossed with a hybrid. And if you're looking at the same trait, actually what you get when you cross a hybrid with a hybrid is that half of the offspring are going to be hybrids, and then the other ones will be just like the parents. And if you want to know more about that, we do have a video that is all about Mendel and his aliens.
So this is going to be one of our future topics that we're going to do.
We'll go into more detail on genetics in a future episode, but I wanted to just show you, kind of answer that question to say, if you want to know more, watch that video and it will explain more about why we don't have a special word for hybrid crossed with a hybrid, and how when you do that, you often get different results. You can get a wide variety of traits, which is kind of fun. And then we're going to take two more comments from our chat here. And I have asked Science Mom Krista and Emily to be kind of giving me some questions, because it goes by so fast it's hard for me to look. And I have to say, one of the most excited texts that I got today from Science Mom Krista was that somebody did your song in Morse code and posted it in the chat. Which is outstanding. So way to go.
That's nice. So I did see a comment asking, can you explain that heredity thing a bit better? Let's just say it will be upcoming on another day. We'll talk about how traits are passed along and inherited.
And if you watch the Mendel and his aliens video, that little video that we did on it will explain it a lot more. We have a whole video about that, but we will cover that more in the future. Yeah. And then another question that relates to smell is, why do onions hurt your eyes? So when you slice an onion, we've probably all experienced that you can smell that pungent onion smell, which also has those sulfur compounds. And why does that make your eyes water? That is a great question. I actually don't know the answer, but I'm going to make a little note that will be one of our 5 questions that we will answer tomorrow.
It's probably like wee little gremlins that are
in the air. It is not wee little gremlins, I'm sure of it. But I'm looking forward to researching and finding out. We will answer that question tomorrow. Another good question that we got is, are coconuts nuts? And again, it all depends on your definition of the word nut. If we define a nut really broadly as just a hard covering that has something inside that you can eat, then so many things are nuts. And so it all depends on how you define nut.
So are there other foods then, like asparagus, that some people can smell and others can't? Is that a thing?
Yes. So smell, there is quite a bit of variability in smell. Certain people have stronger senses of smells than others. And then certain animals, like we said, can smell better than others. So dogs can smell things that we can't. And they can smell a lot of things that we can't.
Was that somebody asking what time did we start our live stream? So we're doing 8 a.m. Pacific time?
8 a.m. Pacific time. Yep. And then before we show the drawing prompt, I want to share just a few more of the entries that we had yesterday, because we had some outstanding ones. And one of my favorite photos that I saw was actually this one of 2 kids looking out their window, drawing, and then they're getting ready to add the fantastic thing. I thought that was a great picture. This one here was a really great one. Thanks for sending that in, Katie. And then we had a couple great ones with dragons outside. So look outside and see a dragon, which I love.
You guys learn to draw so well. Man, is this like a class at school they have? Because I must have missed that class.
Math Dad often says he wishes he could draw better. So he's very impressed with your art skills.
Yeah. I think it's probably like anything. If you ask, where did he learn to play the piano so well? He must have just been born with it.
And
no.
Practice.
Yeah, it's practice. I think practice is the answer to most things in life.
Practice definitely is. Our prompt for tomorrow is to design your own labyrinth or maze.
So this is maybe a secondary prompt. It kind of goes along with the math question, except for the math question, you wanted to do a simple maze where you were just counting the number of paths to get you through. And in that case, you don't want it complicated with lots of dead ends and things.
But with your maze that you draw, what I would really love to see is draw who is getting through your maze and what are they trying to get to. Because there are a lot of possibilities here with why there would be a labyrinth, what there might be in it, what someone's trying to find. So when you make your maze, be sure to write down a little bit about what is at the end. Is someone looking for treasure? Is someone trying to escape? Is it for an animal, a maze for an animal, or for a person, or for someone else? So have fun with that. That's our drawing prompt for tomorrow. And again, you can post these to Facebook on the Science Mom Facebook page. I'm going to put that same image. So look for a post that has this image. And then in the comments underneath that, you can share your pictures and you can see the other incredible things that other families are coming up with. Or you can post it to Instagram and then you can tag me at the Science Mom, or you can use the hashtag Science Mom Squad.
Is that post already there on Facebook?
No, but it's going to be right after we finish this live stream.
Yeah. You kids are fast. We get submissions before the show's even done sometimes.
Yeah, it's just been incredible. I've got to say, we had no idea that this would grow as big as it has, with thousands of people watching each day, and it's just been amazing. So I want to give a special thank you to everybody who is watching right now, and to everyone who has shared it, who has posted on social media and invited other people to join. That is it's the most amazing thing for us.
We had a request from a mother who said that their 2nd grade child is supposed to know their addition and subtraction facts all the way up to the number 20. And if I had any suggestions there, and the answer is yes, I do have a game that I want to recommend. Ooh. So everybody knows the game of memory, where you've got your little cards upside down and each person takes turn flipping over to seeing if they got a match. And if they got a match, they get to keep the cards. And if not, they just turn them back over. And then the next player gets their turn. So what I would propose is try playing the game of memory, except your cards would have, say, the numbers 1 through 20. And what it means to get a match is you have to get 2 numbers that sum to 20. So they have to add up to be exactly 20. So for example, the match to the number 8 would be the number 12. So if they can get both the 8 and the 12, and they have to do the math to figure that out, then they get the cards. So yeah, and so it's the same skill set, it's the same game of memory, but
with a little extra twist, because there are multiple combinations. So you don't just need to turn over the 8 and find, a matching 8. You turn over the 8 and then you've got to find, and you could do multiple sets of each number. Yeah.
So if you want to motivate your kid to care about what number plus 8 gives you 20, a game like this would provide some good motivation.
You know what? You have a lot of good math games, and we haven't even included that. I think we should make that a regular thing. We can show you a fun math game to do every single time.
Yeah.
Yeah. I'm going to head back over to the chat real fast and just see if there are any questions before we finish up. Can you put coffee beans in your garden to keep bugs away? That is a great question. I don't know that would work. Okay, so I will say the coffee beans, if you put coffee beans in your garden, like the coffee grounds, that works really well for just the compost and adding nitrogen to the soil. I don't know that there's enough caffeine left over in the grounds to have an insect repellent effect, but if there is, it definitely would help reduce grubs. And then we have a math question.
So
this is a good.
There are 5 trucks in a construction site. They run 24/7. The workers there have to work 5 days a week, 7 hours each day. How many workers are there needed to run the trucks if each worker runs 1 truck?
Should we turn around to the whiteboard and you do it real quick? I'll go back to the top one.
Well, actually, so there's a little bit of a problem is I don't think we have enough information, but if there are 5 trucks, so they want to run 24/7. Maybe there is enough information. So we would need to know. Oh boy, yeah, we can figure this out. So they can work 7 hours a day. So how many times does 7 go into 24? So there's almost 3.5 shifts per day, and so in that case,
should we draw it out on the
5
whiteboard?
trucks. Is there a number of workers? Do we know the number of workers? Or is that what we're asking?
That's what we're asking. How many workers? So 5 trucks in a construction site. They run 24 hours a day, 7 days a week. The workers there have to work 5 days a week, 7 hours each day. We're not getting very friendly numbers.
Okay. So.
And then how many workers are needed to run the trucks if each worker runs 1 truck?
All right. So what I want to know is we've got the total hours that we're going to need in a week. So that should be in 1 week. So there's 24 hours a day, 7 days a week, 168 hours in a week. So can't even see this. All right. So there's 168 hours in a week, but we're going to divide that by the number of hours that an individual worker can work. So that was 7 hours a day for 5 days a week. So 35, and this is hours.
And that's how many one worker can work in a week.
That's right. So 35 hours per worker. And then if you take the time to do the division, so what's going to happen to the units? You're going to hours divided by hours per worker. So when you divide by a fraction, this is going to flip over. We're going to get a decimal answer.
4.8.
Yeah. Okay. So 35 goes into 168. So 4 times 35 would be 140, and then I would leave 28 left. 28 over 35. 4.8, and then the units are workers. All right. So that means it takes 4.8 workers to run 1 truck.
If you want to run that truck the whole entire week.
To run that truck for the entire week. So there were how many trucks? 5 trucks. So in this case, I'm tempted to just multiply this number by 5. You get 24. But I think you probably need to round up. You need a 25th worker because people can't work more than the 7 hours. And so we'd need at least a 5th worker. Now, would that work even? So 24 is obviously the lowest number, but then you'd actually have to make sure that these are coming in whole number units because you can't use fractional workers to keep parts of trucks going. But man, maybe you can probably arrange the shift so that people are switching out which truck they're going. I maybe as few as 24, but it's possible we'd need to round that up to 25. So that's a really good question. It's the type of thing you just start playing with the numbers, try to think, would this answer my question? Would that answer my question? And you'll notice I didn't know the answer to start with. For that matter, I'm not even sure I'm right now. I'd actually have to try to map this out. Can we actually schedule the workers and stagger them or combine them in such a way that this works out? Because I think if you started all the shifts at the same time, you probably need to round up to 25 workers. If you stagger them in a certain way, maybe it can be done with 24. But maybe I've missed something. maybe it's more complicated. Scheduling is a difficult thing, but that's something a boss has to be able to figure out for his employees or her employees.
Great question. Can you make a maze in Minecraft? You definitely can. If you are, for our art prompt, making a maze, if you want to do your maze in Minecraft and then take a screenshot or a picture of that and post that, you definitely can.
Or for the math problem.
Yeah, or for the math problem. If you're working on it, yep, definitely. Oh, when did I get inspired to study science? I have loved science ever since I was a little kid. And I have to say, a lot of that love came from just spending time outside and being curious about the natural world around me. How do plants grow? What is dirt really? Like, what is dirt made of? Why does some dirt look different than other dirt? These were questions I had as a little kid, and I went looking for answers. And that's what first sparked my love for science. We have another question. Is blood blue or red? Human blood is always red. This was one of our fact or fiction things on our first day. And I have a whole video called What Color is Blood Really that you can check out for that. Show more outside the window pics, please. We have so many fabulous outside the window pictures. And I would say look on Facebook, on the post we made on Facebook, because there are so many wonderful pictures there. And you can also look on Instagram. And going forward, I'm going to ask everyone to use the hashtag Science Mom Squad, because that will be a little easier to find than the hashtag Quarantime. A lot of people are starting to use this hashtag, but I think Science Mom Squad is going to be one that is a little easier to use.
Will you see if you can open up your Facebook and you can share your screen for the leprechaun traps and things? Let's see if we can.
We'll try. Will this work, guys? Will we be able to share our screen?
Yeah, in our attempt to share screens, but that's because we were also switching computers. So there's literally a button in this program that we're using. It's called StreamYard, and it's letting us stream to both Facebook and YouTube. But yeah, there are a few technical difficulties and some limitations that come along with it. So Science Mom is currently scrolling on the computer, trying to find the Facebook page, and maybe we'll be able to share some.
But part of our issue is if we open up too many things too, we might have lag and then start slowing things down because we're using more of our internet. So it looks like this might be taking a while. I think what I will do is I will get a screenshot because I could see that things started to go slower and I don't want to interrupt the quality of our stream too badly. So I will get a screenshot and have that ready for next time to show you where that post is, where you can see more outside the window pictures. And I will say we saw such amazing art. And I asked Science Mom Krista to pick some and make slides, and those were the ones I shared. And I know for both her and me, it's hard to only pick a few because we want to just share hundreds. We will share more in the future. I think we'll figure out a way to do a little slideshow at the beginning and the end so that we can showcase more of the art because it's really fantastic. You guys are doing an amazing job.
That's right. So post them on Facebook, but also look and see what other people's art looks like. See what they've drawn. Maybe it'll give you some ideas, but you can also tell people what you like.
Oh, we're having some great questions here. You know what? This question about the ping pong. Oh, whoops. Where do hybrids come from? It goes so fast. Sometimes it's hard for me to pick the right one. There was a question about the ping pong ball. We will revisit that later, and I'll see if I can get some video clips prepared in advance so that it will work for a live stream. And we will do one more quick math question, and then we've had several requests to sing the song. So we will sing our song again before we leave. I think your song's going to become a thing. He's very proud.
I'm singing a song, I don't know the words. I don't know the words to this song. I'm singing it loud and I'm singing it long, but I don't know the words to this song. No, I don't know the words to this song.
And last quick little question, how do you multiply fractions? So this is going to be our last question. We'll go to the whiteboard again, answer this, and then we will do our little closing note and we'll sing the song again for you.
All right, so how does one multiply fractions? So we won't do a big lesson here, but I will do an example. And it turns out it's easier to multiply fractions than it is to add the fractions, as long as you already know how to multiply whole numbers. All right, so suppose I had a fraction like 3/7, and I wanted to multiply that by a fraction, say 4/5. all I have to do to multiply those, I should use a darker marker. Let me try that one more time. 3/7 times 4/5. All you have to do is multiply the numerators. 3 times 4 is 12. And then on the denominators, the bottom parts of the fraction, 7 times 5 is 35. So that's just one step on top, one step on bottom, and it can't be simplified. There are no common factors here. We are done. So, I mean, there's a lot more to the lesson, on this than just an example, but it's actually not too bad to multiply fractions.
What about adding them?
Well,
what if you were going to add those two fractions?
Okay, so if you wanted to add two fractions, let me give you the quick version here. We would need to rewrite this problem. So if we had, think of these as pizza slices. So if you had 7 slices of pizza and you wanted to just get 3 of them, and the other time you're breaking the pizza into 5 slices, those are different size slices of your pizza. So you can't actually compare those. So sorry, we're trying to change this into an addition problem. So first of all, we just have to change the way we write each fraction. So in math, there's not much that you're allowed to do. You can always add 0 to a number, or you can multiply a number by 1, or you can replace a quantity with something that is exactly equal to it. If you're doing anything else, then you're on shaky ground. There's really not much that you're allowed to do. So every operation we do is just replacing something with something equal to it. Or maybe you're adding 0 or you're multiplying by 1. And it's usually just some variation on those things. All right, so what we would need to do is figure out how many slices would we have to cut this pizza in so that we could compare. And in this case, our common denominator, we look at the 7 and the 5. We say, what's the smallest number that those go into evenly? So you probably not learn something like this till at least 3rd, 4th grade. But so for the younger kids, this is going to be harder. But so 7 times 5 is 35. All right, for this first fraction, we're going to cover up the second one. 3/7, I multiplied the bottom by 5. So I'm going to multiply the top by 5, which gives me 15. So really what I multiplied by was 5 divided by 5. I multiplied by 1. So that's why that was legal. One of those things I said you're allowed to do. All right, the second fraction, I would also want to multiply by the number 1, but I would multiply the top and the bottom by 7, because that's going to need to get to 35. So 7 times 4 is 28. That's an 8.
It is now.
Yeah, okay. So now that my slices are the same size, pizza cut into 35 pieces, sounds so delicious. All right, so I add, now I do 15 plus 28, and that will give me 43. So we had to go through several steps to get here. Adding the fractions is actually harder because you have to make sure that these denominators, that the size of your slices match up. So obviously there's much more to that lesson than I could give as a quick explanation.
Thank you, Math Dad. And I gotta say, we are, come over here with me again. This has been probably like the most incredible week of our lives, minus like big events like having kids and things like that. Like, you know, becoming parents is, I don't think there's anything more meaningful or life-changing than that. But this has been really life-changing for us to have our channel go so big and to have this connection with you guys. And we would love your input. I'm going to create a couple little polls over on Patreon because there are a lot of different things that we could do with this in the coming weeks. In Nevada, we know that for sure we're not having any school for the next month. There's going to be a whole month with no school. And so we would love to keep this going. And for science, I'm planning out little lessons on like 1 month to do chemistry, another month or week to do biology, and we'll go through different science topics. But for math, there are so many different directions that we could go. And we would like to kind of get your input about what topics you would like us to cover and the format. And I think we will definitely do some more games and things too, math games. And, oh, Margaret says, why does this have to end? No, we will be back again tomorrow. And tomorrow we're going to be talking about the scientific method. And if I could find Mentos and soda at the store, last I heard they still had Mentos and soda, we're going to see if we can get this live stream set up right outside our garage so that we can show you some Mentos and soda action tomorrow. So that's going to be a lot of fun. That's what we're going to be doing tomorrow. And that's going to be, so scientific method is going to be the subject of our next video. And then on Friday, we're going to do a kind of a fun day, a Friday fun day. We're going to do a bunch of challenges. If there is a challenge that you want to see Math Dad and I do, then please tag us on Instagram and tell us what the challenge is. Our inbox right now is so full, like don't email us because I have more than 600 unread messages in my email inbox and I'm just not going to be able to see them because I have to get ready for tomorrow's live stream and spend time with my own kids. And so don't email me, but if you tag us on Twitter or tag us on Instagram, those two places I feel like I'm still able to keep up. I'm trying to get caught up on Facebook. If there's a challenge you want to see us do on Friday, let us know because we're going to do some games and challenges on Friday. So that is what is coming up the rest of this week. And again, you guys, this has just been amazing. We will, we have another request to sing the song again. We will sing the song and then I will give my you exist thought that I like to share at the end and then we're going to be done. So here we go with the song.
I'm singing a song, I don't know the words.
I really don't
know the words to this song. I'm singing it loud and I'm singing it long, but I don't know the words to this song. No, I don't know the words to this song.
Let's sing it again. This time maybe I'll get the words right and you can do harmony. I'm singing a song, I don't know the words. I don't know the words to this song. I'm singing it loud, I'm singing it long. I don't know the words to this song. I don't know the words to this song. Definitely better when you do that melody. We'll keep it that way from now on. And our closing thought is that you take a minute to just think about the fact that you exist and you are a human being. You're part of a human family, and that is a beautiful and amazing thing. Consider something as simple as this can of corn. If I was on a deserted island for 50 years and you told me that all I had to do was make a can of corn, I wouldn't be able to do it. Not if I was just by myself and I had no internet. I wouldn't have the machinery to get the steel, form it into a can, put the corn in and pressurize it. That requires so many things. And it's really a beautiful thing to be part of this human family. And I just want to take a minute to say thank you for joining the Quarantime family and being here with us today to learn about math and science, play games, and sing a song that we don't know the words to. We really appreciated having you here today, and we will see you again tomorrow.